Hey everyone, today we're talking about interior angles of a polygon. Here is a hexagon. So the interior angle of a hexagon would be like this right there. That would be the interior angle. And so we would like to know how many degrees are there total in any polygon. So what or how do we figure this out? So if you can recall how many degrees there are in any old triangle, there are 180 degrees per every triangle, no matter what the shape looks like, no matter if it's an obtuse triangle, a scalene, isosceles, or equilateral. All triangles have 180 degrees. So you could think, let's break this shape, this particular polygon, this hexagon, into as many triangles as we can. Now, I would like to do that from, let's say, this vertex here. Now, if we break it up, we can make a triangle that way, another one if we go to that vertex, and another one to that one. So if you count that up, we have 1, 2, 3, and 4 different triangles. So if 4 triangles, and each triangle has 180 degrees, that would mean that a hexagon, and this particular one, and all hexagons, have 720 degrees as a sum of their interior angles. And that would be true. So what do we get to figure out from here? Well, you might be thinking, well, why did we draw the triangles that way? Why didn't we not just go from the center point, right? So you could think if you had some sort of hexagon and you have a center point and you make all the triangles from the center, going from the center to every vertex, you would have then 6 different triangles. And if you think about that, remember we're trying to find like this particular one right here. We're trying to find this right there. We're trying to find all the interiors. So that one plus this one plus this one, that one, this one, and finally that one. We're trying to add up all of these being different interior angles potentially, and we would like to know how many total that is. And the total we figured out was 720. But how are we going to get that over here? And if you think about that, that would give us 180 degrees, because there's 1, 2, 3, 4, 5, 6 triangles, and 6 triangles times 180 gives us 1080. Now, that is not an actual representation of what we just did. How does 720 give me 1080? Well, there's something we didn't think about. Interior angles are these angles right here that are on the edge of the polygon. Central angles, on the other hand, are these angles right here towards the center. Central angle right there. And so there are 6 central angles. And if you think about that, we are going all the way around. And if you did not already guess it, that is a circle. And so that's 360 degrees in the central of the interior. So we don't want that. So we'd really be taking 1080 and subtracting 700. Oh, actually subtracting 360 degrees, and we would get again our 720 degrees for our interior angles. Now we can kind of figure this out, and I will show you from here how we figure this out. But what if if it is a different polygon? What if we have a different polygon? What if we have a quadrilateral or a pentagon? Well, let's see what happens. So if we have a quadrilateral, any old quadrilateral, we'll draw a little funkier, draw it like this. You could then choose a side, choose a vertex, choose a vertice, and we make our triangles, and you can see, ooh, that is a curved line. Let's do that again. We make a vertex to vertex segment. Close enough. We have 1 and 2 right there. So that would be 2 triangles times 180 degrees. And that gives us 360 degrees. And if you go up by 1 and we make a pentagon, well, then that pentagon, we can go from a different spot. Let's say over here, we've got 1, 2, and 3. So 1, 2, and 3 triangles. So that's 3 times 180. And we get 540 degrees. So if you think about it, we can actually draw like a little table here. and this is number of sides, right? So we can have number of sides over here, like we have a 3-sided figure, right? Number of sides right here, and 4-sided, and 5, 6, etc. And how many triangles we had, and then finally the number, our final number of interior degrees, right? Remember, we're trying to find the interior degrees. That is the whole purpose. So in a triangle, we know that if there's a 3-sided figure, well, that's one triangle, and that would give us 180 degrees because that's a triangle. And a 4-sided figure we just did right here gave us 2 triangles, and that gave us 360 degrees. And we had a 5-sided right here. So 5-sided gave us 3 triangles, and 3 times 180 was 540. And earlier we did 6, and that gave us 4 triangles, and that gave us 720. Now, it would be really nice if we had some sort of pattern that we could get, and we could figure out what any number would be, like a 20gon or a 50gon or a dodecagon. So how would we figure out what a dodecagon is? A dodecagon is a 12-sided figure. So if I want to know what a 12-sided figure is, how many triangles does a 12-sided figure have, and what is the total number of degrees a 12-sided figure has in the interior space? Right now, I would like you to pause and figure this out before I give it away, but I will be giving it away if you do not pause. Okay, so if you notice, we are going up by 1 side every time, which is increasing our names. We went from triangle to quadrilateral, pentagon, and then finally hexagon. And if you noticed, the difference between the number of sides and the number of triangles is a reduction of 2. So how many triangles would a dodecagon have? Well, the number of triangles would then be 10 triangles. And how many degrees would that be? Well, if you can think about that, 10 triangles where every triangle is 180 degrees, that would give us 1,800 degrees. That is 10 triangles times 180 degrees for each triangle gives us 1,800 degrees. So how do we know that? What is a pattern? How can we figure this out if we're thinking about a formula? And here's the formula for you. The formula is n for number of sides minus 2, which is exactly what we did first. And then what did we do? We times that. We multiplied by 180 degrees. And that is our formula for interior degrees, the sum of the interior degrees of any polygon. So, that being that, what about the exterior? Now, if you remember, as I erase all of this work that we have done, if you remember, we talked about triangles, and you've probably talked about triangles in your classes. We had an exterior angle theorem. It's actually one of my favorite theorems. It gives a lot of information with only doing a little bit of work, which is right up my math major alley. So, an exterior angle, when you go back to triangles, the exterior angle theorem, if you extend this angle out, this was the exterior angle right there. And if we call this angle 1, then let's say this is angle 2 and this is angle 3. The exterior angle theorem said that angle 1 was equal to angle 2 plus angle 3. And that was our exterior angle theorem. And what that meant was that we had 180 degrees in a triangle, and there's also 180 degrees in this straight segment here. So we used the proof to show, and I can show that another time, that both of these are equal to 180, so therefore angle 1 is congruent to angle 2 plus angle 3. So angle 1 is our exterior angle. So how many degrees are there in all exterior? So we have a formula for the interior, but what about the exterior? So if we go back to some sort of quadrilateral here, let's draw something like this. and we want to find this exterior angle here. Well, how many degrees are there? Well, we want to know how many degrees there is in that one. We want to know plus this one. We want to know plus this one. And finally, we want to know plus this one. So, how many degrees if we add up angles 1, 2, 3, and 4? How many degrees are in all of those? Now, I beg you to try and figure this part out. And I'm going to give you a hint. So, this is a quadrilateral. A pentagon looks like this. I'll try to draw these a little bit more regular for you. And a hexagon looks more like this. And let's even go an octagon. What would a 20gon look like, or even a dodecagon? What shape are we getting closer to? Are we approaching as we can increase the number of sides? What is it going to look like? What is it going to get closer and closer to? And I'll pause. If you guessed it, the answer is it's getting closer and closer to looking like a circle. In fact, that circle looks less like a polygon than anything else. So we are getting closer to a circle, and as you probably know, circles have 360 degrees. So the exterior or the sum of, let's write that, let's say the sum of the exterior angles in any polygon is 360 degrees. And again, that is for any polygon. This is the exterior we're talking about. So we're talking about the sum, not just one single one, not just this angle here, but this angle plus this angle plus this one are all going to add up to be 360 degrees. So what does this look like as a quiz? What does this look like as a simple question to ask? We always like to figure out these in simple form so we understand the concept, and then we move to more difficult questions that you may see on a quiz or a test, even a final, even a state test. So what would something like this look like? So a simplified version of this would say something like, what is the sum of the interior angles of a nonagon? Now, what makes this a little bit more difficult? Well, you have to know your terminology. You have to know what a nonagon is. You also have to know that they're talking about the interior, and it's the sum. We're not looking for one of them. We're looking for all of them, and we have to figure that out. Now, if you recall and you took notes, you would remember what the formula was, and I would suggest using that formula, and then you'd also have to know that there is a nonagon is 9 sides, and you would be able to figure this out using the formula. So the formula again being n minus 2 times 180 degrees. So n is 9. 9 minus 2 times 180. That gives us 7 times 180. And does anybody know what that one is? If you got 1080, that would be wrong. You have to go one more above that because 1080 was for six different triangles. And so 1080 plus another 180 would give us 1260.